Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the Keithley DAQ6510, which is a hybrid data acquisition and 6.5-digit multimeter in one box. Keithley has been releasing a lot of new instruments lately. They all follow the same design philosophy with a unified operating system, and I've done quite a few reviews on those. I've done reviews on their source meters as well as their 7.5-digit multimeters. Now they have, of course, the DAQ6510 and the DMM6510. The really nice thing about this unified ecosystem is that they all use the same design language and they all have the same OS and therefore the same capabilities. Not to mention that they are compatible with the same scripting, which is called TSP, as well as the same software on the PC, allowing you to basically create almost a turnkey solution for measurement automation and measurement analysis. And of course, a lot of those capabilities are already built into these units as well. It's really nice to see that Keithley is creating this brand new ecosystem of instruments, and once they get started, it's really hard to catch up with them because, first of all, they are one of the best, if not the best, test and measurement in this domain, being able to create analog measurement equipment, of course, and now they have this nice, continuously growing set of instruments that all follow the same design philosophy. So I'm really happy to see that. I've had this for quite some time. It's just been really busy to make a review out of it, but we're going to take a look at it. We're going to take it apart. I want to tell you some of its capabilities and the different acquisition cards that can go into it, and we're going to design some experiments, as we always do here at the Signal Path, to see what happens to the instrument when you want to use it in some real life scenarios. So there's a lot to do. I can only really cover a portion of its capabilities, but definitely watch the other videos because there's a lot of details in there as well, and you can see some of the other capabilities of the units which I'm not going to cover in this video. But anyway, let's get started. So here's the data sheet for the DAQ6510, and of course, as I said, this would also make a very good 6.5-digit digital multimeter. And here we have some of the specifications and measurement capabilities down to 10 picoamp in DC current and down to 100 nanovolt in DC voltage. And here you have the range for the instrument when it's in digitized mode. At 1 megasample per second, you still have an enormous dynamic range of measurement capability built into it, which is quite nice. You also have down to 1 ohm full scale when you're operating in 4-wire resistance mode. So it is a very capable multimeter, as you would expect. I'm not going to go through the entire data sheet, but I definitely encourage you to go and take a look and also see all the different modules that you could have in conjunction with the unit. So we have here the 7700, which we're going to take a look at, but depending on what kind of data acquisition you do and what kind of measurements you want to do, you can of course choose a different one, and that can be pretty handy because you never know what kind of applications you have. You can mix and match these. There's 2 slots there you can try. But I'm not going to bore you with the details of the data sheet. You can obviously go ahead and take a look at it and see if it suits your application. But more importantly, let's take a look at the unit itself and take it apart. And here's the front panel of the Keithley DAQ6510 data acquisition and multimeter system. Now, as I mentioned earlier, you don't want a data acquisition unit that compromises the operation of the multimeter aspect of the instrument. And this one indeed does not do that. As you can see from the front panel, it is indistinguishable from a multimeter. And all the functionality and ease of use of this unit is identical to a very good 6.5-digit meter. In fact, the only difference is that there is a terminal switch in the front, which is either front or rear selection. You can see it's a push button here, and that is the only difference really. And when you go to the rear, the operating system detects that and influences the way the OS operates, which is great, and I will show you that in just a second. For power button, they're using soft power, unlike the other source meter and multimeters in the same series, which all have hard power buttons. They must have changed the power supply design for whatever reason. They prefer to have the soft power. USB, a few buttons on the left here and a few buttons on the right. I think these are the good choices to have. Home menu, apps, and help. Help is contextual. Apps is a new kind of ecosystem they've introduced in the operating system of these new instruments. We'll take a look at that. It's quite interesting. And the enter, exit function and trigger, which are the buttons that you would want to use quite frequently. The LCD screen is a multi-touch capacitive, very bright, very high resolution, just like the other source meter and multimeters systems they have, except it is now recessed. And I like it. I think I like it a little bit more. It's more defined. The edges are a little bit easier to kind of see from far away. So it looks good. And the front, of course, has the typical high and the sense, the 4-port and the current. And this one supports 3 amps. It would be nice if it went to 10 amps, but 3 amps is fine for most cases. Other than that, looks good. Legs lifts up, looks exactly like the other units from kind of a design philosophy, which is great. It goes with the rest of the modernized look of Keithley. Let's take a look at the back. And here's the back of the unit. As you can see, simple power input, 2 module slots. One of them I've removed, so you can see how deep it goes. These are fairly large. We'll take a look inside one of these as well. And this card here is interchangeable with several different functions. This is optional, unfortunately not included. So the TSP link is an additional card you have to purchase, as well as the digital I/O. But Ethernet, USB, trigger in and out, those are all basic functions that are supported on any of these units. It's nice to see that there's 2 slots. It's typical to have 2 of them, and this gives you flexibility to mix and match and put 2 different types in here, and of course all fully accessible through the operating system. Looks good. Let's go ahead and take a look inside one of these guys, and then we'll take a look inside the unit itself as well, and then we'll turn it on, do some experiments. And here is what is inside the Keithley DAQ6510. This is a top PCB, and it is beautiful. Just look at all of this wonderful analog and mixed signal engineering that's gone on to this board. Let's talk about some of the interesting things that pop out when we look at this. Let's start from this corner. This is a pluggable card. This is the TSP link card. It has its own lattice CPLD on it and some I/O controls. This is an optional card that you can plug in, and once you plug it in, there is an interface connector here. So it's very straightforward. There are several different types of these cards which you can have doing different things, all sharing the same kind of interface. But if you also look carefully, you can see that there's a very clear cutout in the copper port on the board itself, and this gap over here provides isolation from everything that's digital, and more importantly, everything that has a human interface from the main analog board. Not only do you want to isolate the main analog board from all the digital activity that happens on these components, but you also want to separate them from all the high voltage that may be applied to the unit. You don't want any of that to creep and potentially couple to anything outside of the unit itself. Over here we have some more, there's a bridge rectifier tied to the chassis here for thermal, and there's some triggers and USB as well as Ethernet ports over here. That makes sense. All those signals are then routed over here, which then connect to this little portion of the board, and this portion of the board is interfaced to the front panel LCD. Now this front panel LCDs are more than just LCDs. This is a full application processor or operating system running into it. It's essentially a computer that interfaces with everything else, and everything runs on this, and when you update the firmware, you also update this OS built into this. As far as I can tell, I can't see any other application processor. It may be on the other side of the board, but nonetheless I believe everything is running on the screen here. And you can see cutouts in the board to further improve isolation, and you can see that we have a few components across the cutout board. These are high-speed up to optically coupled I/O interfaces to send signals back and forth, so you can essentially control this entire region directly from these tiny little interfaces, and there's some more over here as well. And these cutouts are really obviously well engineered and engineered with purpose. They're not just randomly placed. Depending on where the signals are, what kind of signals are across them, they have been designed to handle those. Furthermore, you can see a connector here which brings power most likely into this entire region. The power supply is on the other side of the board. But if you look carefully, this thing actually has a fan, and the fan is right over here, but it's underneath this board, and it's very cleverly placed because you don't want any air flow on top of this board. You don't want the temperature over this board to be unknown, because you don't know what the ambient temperature is, and you don't want the fan to blow air over this. In order to keep everything here at a constant, predictable and uniform temperature, they have made sure that the PCB hugs the chassis in such a way not to have any air exchange from the fan. So the fan underneath this area only cools the power supply, which you don't see of course here because it's on the other side, and you can only see 2 connections where power is brought into the board. So a very clever thermal design of an instrument like this is also necessary. Another thing to note is that this has the same footprint as a regular multimeter, but most of this chassis has to be empty because the pluggable modules, here's an example of that. You can see how big these pluggable modules are and how thick they are, and there's 2 of them. Therefore, you have most of this chassis empty, so the power supply is confined only to this region. The rest of it is the plastic enclosure which accepts the data acquisition modules. If you look at some of the analog functions, we can see here is the lattice CPLD that also is responsible for the interface. It may also be responsible for the multi-stop data conversion and so on. I'm not sure. There may be a dedicated A to D converter. We can dig into that and find it. But we can get a rough idea of the architecture. Here is our linear reference there. That's a very common thing. These things have a built-in oven, selected and tuned and aged and so on. This is a very common knowledge with multimeter design. We have our input protection. Now the input circuitry here is really important because unlike a regular multimeter, you don't just have the front panel, but you also have to reliably and with high degrees of repeatability switch the input terminals to the acquisition board on the other side. It's not something so straightforward. Here's the connections you can see here These connectors are the IOs that go into the data acquisition boards on the other side. And they're very close to each other, and they have the necessary cutouts to protect them from each other, as well as from leakage from port to port, and to be able to switch them back and forth to the front panel inputs, which are these, and the ports that go to the other side. And this long device here, you can see this switch that I can switch back and forth, is what does all that switching. So the input has to be switched using these little network here. So there's a lot of work that's gone into making sure that that's repeatable and reliable. Gas discharge tube, different kinds of protection. There's a big fuse over there, another gas discharge, high-speed, high voltage series resistors, and a fluke laser trim precision resistor array that you may not see from that side, but it's glued to one of the components so that it doesn't vibrate and shift. You never want to touch these or move them, because then you throw away the calibration, of course, of this unit. Even though this is only 6.5, and I say only 6.5, you don't want it to have drift. A 6.5 digit, you don't want it to have drift, of course. And everything else is very nice. Lots of analog devices and components over here, and op amps and so on. All the functionality of a typical multimeter. But the general architecture is really nicely well put together. The board is fantastic layout. Everything is beautiful. Again, this Keithley, what else do you expect? This has to be this good. Some components underneath this over here, I'm not sure what exactly is happening, but there's not that many things on the other side. Maybe just for isolation or for high voltage protection and so on. Or maybe even a heatsink from the other side. So other than that, looks good. Let's go ahead and put it back together. I'm eager to turn it on, play around with the GUI, show you a few experiments, and then see what we can do with the data acquisition. Let's go ahead and take a look at one of these pluggable modules. This is the Keithley 7700, one of the many different pluggable modules compatible with this data acquisition instrument. And I'm going to take the front off. Of course, you're supposed to be able to do this when you want to connect something to it. Single screw, pretty straightforward. So the job of any pluggable module in the data acquisition system is to time multiplex many inputs to the same common 5 terminals in the front of the instrument that you see and typically use in a multimeter fashion. Now this sounds very simple, but there's a lot of things to consider. How reliably are you routing the signals? How configurable the data acquisition module is? What is its lifespan? How much bandwidth it has? How much isolation it has? So we're going to talk about a few of those. Now the first and most important thing is whether it's a solid state switching or electromechanical switching. Now this is of course electromechanical. That has a lot of advantages, its reliability, its linearity, and so on and on. Of course it has limited life as a consequence. So the choice of relays is pretty important. And they're using NEC. These are Japanese made electromechanical relays. These are pretty much some of the best you can get in the world. And they have very long life. And these are latching electromechanical relays, and latching is important because once you switch between the two states, the relays don't consume any power. Aside from having magnetic fields around, you also don't want them to get warm, because the entire module getting really warm because all these mechanical relays are turned on is going to throw off some of the cold reference junction compensation that is done for thermocouple measurements. So these are all the right choices for this. Now this particular 7700 module has 20 independent channels that you can use for 2-wire measurements, or you can configure those 20 channels and use 10 of them and do 4-wire measurements. And that makes sense, because if you're going to do 4-wire measurements, you're going to need twice as many relays for the same connectivity. There's also 2 independent channels, channel 1 and 21 and 22, that allows you to do current measurement, and they're protected by local fuses, and this gives you 3 amp fuse protection there, so you can get 2 current measurements at the same time. Now this is particularly engineered for thermocouple measurements, because this is one of the very important applications for data acquisition, to monitor and measure temperature across, let's say, an entire mainframe that you would want to monitor, or because of thermal behavior, fans, and so on and on. It's very common to do that. Now, as I said, the lifespan of these relays is critical. Now, these ones are rated for 100,000 actuations at full load, or 100 million actuations if there is no load. And that kind of makes sense as well, because when you have load through the contacts, it's the contact point that's failing, not the electromechanical behavior itself. And they're rated at less than an ohm degradation of contact at the end of life, which is pretty good. And then there you can measure, and all the specification of how much offset current and so on these introduced into a measurement. These are all in the data sheet, so I'm not going to go over them. But they are rated to 300 volts if you're using them for voltage measurement. Now the other thing is, of course, you're going to be using these relays at different rates. Sometimes you're only using a few of the channels, and that causes some of the relays to age faster than the other ones. there is an EEPROM here, right over here, and this EEPROM is going to measure how many actuations these relays have had, and that you can access from the instrument. So you know which ones are close to the end of life, and then you can also balance out how you use them so that you get the most life out of this unit. That's pretty important. The rest of the circuitry you see here are what is needed to switch the relays and some optocouplers to do isolation. Another important thing is that you have to do the cold junction reference compensation for the thermocouple measurements, and there is 1, 2, 3, 4, 5, 6 temperature measurement units directly built into the board. And if you look carefully, you can see that they all share a heavily metallized plate of copper that's on the PCB to even out the temperature across these regions, to give you as much of a uniform temperature measurement as you can. Ideally, you would want to have, of course, many more, but then that'll just increase the cost and the complexity of reading all these things and putting more devices. So with 3 on each side, you get kind of a good idea of the temperature across all of these terminals, which are the terminals you're going to be using to connect thermocouples to. Other than that, I think it's pretty straightforward. Everything else looks good. I think this thing has about 50 megahertz of bandwidth, so you can do frequency measurements with it. There's a complete diagram of the interconnectivity of all these relays is also available, but that's also available inside the unit. So you can configure it directly from the instrument itself, as we will do when we do some experiments with it. Other than that, I think that covers it pretty much and looks very nice and engineered exactly. This is one of the things that Keithley does best in the world. They've been doing this for so many years. They know exactly what they're doing. And these screw terminals have very large screws. This is really helpful. You don't want a tiny screw, because when you want to connect this in the lab, you don't want to look for a screwdriver that's basically useless for everything else except for these terminals. So it's nice that they pay attention even to these tiny little details. So let's go ahead and take a look at the unit 2, and then we'll do some experiments. So let's go ahead and turn it on and see how long it takes for it to be ready for measurement. Now obviously it's going to have to boot up and bring the entire operating system up before you can use it. And it's surprisingly fast. Remember, everything is running directly on this little LCD module, which is the front panel, and it does a bit of self-test and everything during power on, which is necessary for an instrument of this complexity. But there it is. You can see it's up and running. Now right now it is select to rear, which means that it is operating in a data acquisition format. But if you want to just use it as a multimeter and you switch to the front, the OS just detects that and brings you into a front panel of a regular multimeter. So now you have essentially what is indistinguishable from a 6.5-digit meter, with all the bells and whistles that come with the new Keithley line of multimeters. Now I've done extensive reviews and looked at exactly how this GUI works. It's very nice, and it's been improved quite a bit since the very first version came out. The operation is quite a bit more smooth, and then the buttons and the selections and the way the OS just works internally has been fine-tuned and refined based on all the feedback from the users and bugs that have been reported. So it works really well, as you can see. Here's our statistic analysis here. Here is our secondary display, which you can set, for example, to be temperature. In this case, it's not selected to be anything. And then all the different functions of the multimeter itself. Then you have the settings of whatever measurement you're in. Right now, for instance, we are doing 1 NLPC. You can just easily change that to 5, which then, of course, the measurement rate is going to go down because it's now synced, doing multiple measurements within each line frequency. So let's see, here's our graph, which you can then maximize and then do a whole bunch of different kind of looks and zoom in and figure out what's going on. This is very useful in the digitized mode. We will take a look at that. And I've done extensive reviews of this OS with the source meter and other multimeters that I have reviewed. So really have no complaints about this. I think it's come a long way since it was first introduced, and it's just gotten better and better as time has passed. So let's go ahead and see how easy it is to set up a measurement station. So normally in the industry, you would want to characterize thousands or even tens of thousands of components to find out what kind of statistical distribution they have. So here I have a whole bunch of diodes, and we want to find out what kind of histogram and minimum and maximum and variation we observe in the forward bias voltage of these diodes. So you want to do this, you can obviously make one measurement at a time and then put it into a spreadsheet and do all your computation there. But I want to do all of that directly in the unit. So there's a couple of challenges. The first is, well, first of all, we have to make sure we're measuring the forward bias voltage diode correctly. We'll take a look at that. And then we want to find a way to create a trigger mechanism and so that you can go one at a time and measure them one at a time and have some kind of actuation or an external trigger that allows the instrument to move to the next measurement. So here I have just connected a little momentary switch directly to the trigger output or input of this instrument there. There's a port in the back, which I showed you earlier. So we're going to develop and write our own little flow chart here directly in the instrument without using any PC to find out how easy it is to do that. So let's go ahead and measure the diode. So we have to set up the diode measurement. So that's easy to do, of course. You can just go under the diode setting. Right now we're reading overflow because there is no diode connected across the terminal. Let's go ahead in the settings menu and change the NLPC to 3 so we get a little bit more filtered results here. And we have to also choose what kind of bias level we want to apply. Now, luckily for us, this instrument gives us quite a few options. Now, why is this important? Well, let's say I measure my diode at 10 milliamp forward bias. I get the voltage across the diode at a 10 milliamp current, but that's going to heat up the diode because 10 milliamp is still a fairly large amount of current, so you're going to get a thermal effect across the measurement. That makes your measurement much more sensitive to the delay between measurement to measurement cycles. In a production run, it may not be such a big deal because all the timings are exactly the same, but you want to remove that as much as possible. So in this case, we're going to use the smallest current here, 10 microamps, so that we don't get too much thermal effect in our measurement. Let's go ahead and connect it to the first diode. There you go. I'm just going to connect it forward for the 2 terminals from the front, and there it is. There you go. It's reasonable, 0.603 volts forward bias voltage at 10 microamp forward bias current. That is all very reasonable. We can go from diode to diode and continue to make measurements. Now the trick is, how do we set up a proper triggering mechanism and a trigger flow in order to make continuous measurement across all of our samples? So the triggering capabilities of these instruments are truly impressive. This is where they shine, and allowing you to create some really customized settings here. So if you go under menu, and then you go under the trigger here, there are trigger templates built in there, and trigger templates are quite a few options over here, and you can see that even sort binning and grade binning is already included. These things can get really complicated, as we will see. You can pass variables and you can have customization in your trigger directly built into it. Now, I'm not going to start with one of these because I want to show you how it is to build your own, but not only can you use one of the pre-made ones, but you can also modify it once you load it into the memory. So instead, we're going to do our own for now. There you go. We're going to configure here. So right now we have a completely blank trigger menu. So right now you can see the instrument is in idle, meaning that, well, it's idle and it's just going to continue staying in idle. And if I start this, it will essentially do nothing. So let's go ahead and insert a new triggering block. And we have a whole bunch of different options here. So we're going to take an action. And the very first action we want to take is to clear all the buffer, because we want to have a clean memory and we're going to store only the measurements we are interested in. So we're going to clear the buffer. That's pretty straightforward. The next thing is that we want the instrument to wait until it receives a signal from the trigger so that it knows when to do the measurement. That is from the actuating switch that I showed you earlier. So we're going to go insert another block, and we're going to do a wait. And this wait is going to be until one of these trigger events happen. And as you can see, quite a few options there. You can even have an analog trigger when you're in digitization or voltage or current measurement, so that you can find out when there is a sudden change in the analog voltage being measured so that you can do a trigger. This is really useful if you just want to create a lot of measurements, doing a lot of analog voltage measurements across the board, for instance. But for us, we're going to use our trigger in. So external trigger in. And we can configure that whether we want it to be on the rising or the falling. Since we're going to ground it, it's going to be on the falling. We're going to keep that as it is. So our external trigger data is coming from a mechanical switch, not coming from a digital circuit, which means that every time I actuate the switch, I may have a bouncing effect and I may get multiple trigger coming in because it's just a regular switch. So we have to take care of that to make sure that doesn't create multiple unwanted measurements in a row. So that's easy to do. So let's go ahead. After the first wait for trigger, we're going to insert another block, and we're going to do, oops, that's not what I wanted to do. We're going to insert a block of notify. This notify means that once it reaches that, it's going to create a notification within the unit to do something else. So right now we want to create a timer notification. It means that once you get to that, it's going to notify the timer to begin counting. This allows us to create a delay, and the delay is the easiest way to get rid of a bounce condition on a mechanical switch. There it is. We're going to say timer. Let's use timer 1. You can see there's quite a few timers here. There it is. So what's going to happen is that once you hit notify, the notify is going to start this timer. Now I'm going to have to wait until that timer is finished. So we're going to insert again another wait. And this time we're going to wait for the timer, and we're going to use timer 1 as our main event, and we can configure timer 1 to be at a certain count or delay. Delay is a convenient one, delay of 1 second. There it is. So right now what's going to happen is that it's going to clear the buffer, wait for a trigger, notify the timer, wait for the timer of 1 second, and then we have to do something else. So at this point we are ready to actually take a measurement. Okay, so let's go ahead, insert, and we're going to do an action, and this action is going to be measure. There it is. So now it's going to measure, and we're going to say how many times do you want to measure? Well, we just want to measure 1 time. So we get 1 measurement. This means that our buffer is going to be filled with 1 measurement per row. So we are doing exactly 1 measurement per component. Okay, now that we have the measurement per component, we have to make sure that we measure enough times to cover all of our components. Here I have 30 diodes, so we can just count 30 times. So let's go ahead and insert another block, and this time we're going to do a branch. These branches are really handy because you can find out how many different paths you can take, and depending on what's happening, you can go to a different point in your trigger. It can get really cool and really complicated. So in this case, we're going to do a loop counter, which is the simplest one, and we can configure the loop counter to count for 30 times because there are 30 components. There it is. And then it says, well, what do I do if the count is less than the number, it goes through no, and if it's larger, it goes through yes. Well, as long as it's less, you want it to continue doing measurement. And right now you can see it's branching to block number 1, which is not good because that's going to clear all of our measurements. So instead of branching to 1, we're going to branch to 2. There it is. There is our signal flow of our trigger, all built into the unit itself. Now we're finally ready to make measurements. Now the nice thing is that even though I'm going to be doing continuous measurements, I can be in any menu of the instrument during the measurement. I don't have to be in the actual measurement menu, and I'm going to show you. Well, let's get started by setting everything up. I'm going to have my first measurement done of the first diode, so let me hook that up. There it is. And then we can go into the home menu over here, and right now we are not doing any measurement. You can see we're in idle because it's not running right now, but I can go ahead and initialize the trigger menu. There you go. We can go over here and say initial triggers menu. Now it's waiting because it's waiting for my trigger event, which in this case is the actuator switch. I can go ahead and actuate that. And there is our first measurement. So now my first diode has been measured. You can see is one measurement is being done. Now I can move to the second diode, and once I move these clips, I can trigger again. Here's our second measurement, and I can continue on. And if I go under menu here and under reading, you can see each individual measurement being recorded and a little graph being given here. So let me go to the third diode here, and then we're going to actuate another measurement. Here's another one. There it is. You can see it's recorded. So I'm going to continue this and get all the measurements, and then we can look at the histogram. You can also look at the histogram even live as it is being built, of course. There he is. You can see, you can even look at the curve as it's live, as it's being built. This is all possible as measurements are being done, which is really handy. So you can manipulate the screen while all the trigger events are waiting or they're running, which is quite nice. Okay, I'm going to go ahead and do all the 30 measurements, and we can take a look at the histogram. And we're done. There it is. We can see all of our measurements all the way up to 30 diodes, and we can see our plot over here. Let's go and take a look at the data and analyze it a little bit. So we saw the graph already. You can see all the different measurements being done here. That's nice. But really what I was interested in was the histogram. And there's our histogram, and you can see most of the measurements, almost all of them have a nice, and if I were to build more and more measurements, you'd see a very good Gaussian distribution. But I just discovered one outlier. This one over here has 620 millivolt as the bias voltage, which is quite a bit more than everything else. You can see these guys are all bunched up together. There's a few with a low end of about 598, but then there's one guy all the way out there. So then this would allow you to reject that part or to bin it in a separate bin and put it somewhere else. You can also go in here, of course, and look at the statistical data. Over here, you can see the peak-to-peak value, you can see the average, you can see the standard deviation, and the minimum and maximum. You can see that outlier, 620 millivolt, is there. And you can see 30 readings over here. Now you can extract that information, put it into some other computation software outside of the unit if you want to. But really, there's no limitation on what you can do once you have the data. But you can see how easy it is to set up a complex trigger condition and put it all together and then get the data from the unit one at a time. I think it's really nice. So let's take a look at the digitizing capability of this instrument. At 1 megasample per second and 16-bit of resolution, you can extract a lot of dynamic behavior from the circuits you're testing without having to invoke an oscilloscope, not to mention the extra dynamic range you're going to get from this. So here I have a DC-DC converter. It's set to 12 volts right now, and it's turned off. And normally you would be driving, let's say, a resistive load with this. Currently we're driving a very complex impedance with it. It has a lot of inductive components to it. And of course, when I go ahead and enable the output, you can see that it goes to about 12 volts, which is where it's supposed to be. So it's working fine, but it doesn't tell us anything about how it goes from 0 to 12 volts and what kind of waveforms it has and what kind of switching speed it has and what kind of ripple it may have. So let's go ahead and configure this instrument to see if we can capture this at the time where we turn it on. Therefore, we need to have some triggering as well, and then we can look at the waveform during the transition. So let's go ahead and set this up here. Right now I'm in measuring voltage. I can go to the digitization function, and I'm going to change the range from 10 to 100 volts. So right now it's continuously digitizing. If I go ahead and turn the power supply on, you can see we will read 12 volts, and then turn it back off, it goes back to 0. But this doesn't tell us anything while switching. We have to set up a trigger for that. As I showed you, there's a couple of ways to do this, but you can also set up the trigger directly in the graph menu here. I can define a trigger here. This is my graph. It is being continuously measured right now. If I go under trigger, I can define a new trigger. It's going to be a waveform in this case, either an analog edge or a window. A window, you can look at some events happening within a certain window of time or voltage, but in this case we want just the edge. So let's define the edge to be 11 volts. That is right before the power supply reaches its final voltage. We're going to leave the position at 50%, so we can see events before and after the trigger. So now it's all kind of ready. We can go ahead and initiate our trigger condition. There you go. So now it's going to continuously capture data, waiting for a trigger event so that it would stop. So we're going to go and turn the power supply on. And here it is. The power supply is turned on. So we should see now an event. There it is. Check it out. Very nice. Now we see what the waveform was before the power supply turned on, how it got to the voltage you needed to, and then how it stabilized after. So you can see that the dynamic behavior has a little glitch in it because of the inductive load that I'm using to drive it. But we can zoom in a little bit more and look at this event a little bit more carefully. And as soon as I do that, some other interesting features emerge. You can see that there is a little bit of a dip, so there's some startup conditions in this power supply that are worth investigating. And if you look more carefully, you can even see the ripple as the power supply switching noise begins to kick in. And if I can follow that, you can see once it stabilizes that there is still some switching noise. You can grab this data out of the instrument, perform FFTs on it, and then look at it on the computer. It's too bad that it's not built into this, and I think an FFT function in this instrument would be very useful because you can get immediately spectral content of this ultra high dynamic range signal you're capturing from the power supply itself. So this would be quite useful to do. You can also go back, of course, and I can look at the waveform before it turns on, just to show you that indeed when the power supply is off, you can see how much more quiet it is. It doesn't have any ripple as to be expected. So those ripples you see later are indeed from the power supply noise itself. Now all these functionality that I showed you are also applicable to the data acquisition as well. You can do all of these functionalities on the data acquisition channels, even though I've been using the front panel itself. Now that we know some details and operation of the unit, let's go ahead and set up a data acquisition problem and see how the instrument handles that. And here is our setup for the data acquisition. So normally a data acquisition system like this that can have up to 80 channels can be configured to monitor and measure a lot of different kinds of parameters across a wide range of measurement domains. So for instance, let's say you have a rack of instruments or boards in a communication environment and you want to see how the temperature profile changes with the fans coming on and off, with different devices turning on and off, and you want to monitor that across time. So here we are emulating that. We have two loads. You can see two resistors here. We're going to pass some current through them. As a result, they're going to get hot, and we're going to measure the temperature of both of them. I have a thermocouple here and a thermocouple here. They're both going into the unit itself. We have a fan over here which is blowing only on one of these loads, creating a thermal imbalance. We want to study the behavior of that, and this fan is going to turn on sometime during the operation. We're going to monitor the voltage across the fan so we can find out when the fan turns on. We can also look at the current through the load so we can correlate that with the temperature of the system. Obviously the temperature profile of the system is going to be complex and it's hard to know ahead of time, so we can do an experiment to find out. All the relevant information is being captured by this unit, and we're going to configure it in order to be able to get the most relevant perspective of what's going on. I'm only using a fraction of all the channels, but I'm using it to measure temperature, current, and voltage. You can imagine this can be expanded to, like I said, 80 channels and do much more sophisticated kind of measurements. Let's configure the instrument for our measurement. Right now, of course, we're in the front panel still. Let's go to the rear, and nothing is configured, so you're not seeing anything yet. But we can go under the menu, and we can go under the settings of the channel and define the channels that we are using and configure them for the appropriate measurements. You can see that it has automatically detected the Keithley 7700, and that shows you all the connectivity inside that module, which is quite nice. You can see every single one, where they go, what they connect to, so it makes it really convenient. You don't have to go back and forth between the datasheet of the unit. So channel 101 and channel 102, I'm using them as temperature measurements, so we can define them as temperature. I'm using a thermocouple type J, so I can select that, and I'm going to leave all the internal temperature compensation alone. We're not going to have to touch those, but I do want to change the NLPC or an NPLC to 3. There you go, and I want to change the display digits from 3.5 to 4.5. Okay, that looks good. Now channel 103 is a channel that I'm using to measure the voltage across the fan. It's going to tell us when the fan is on and how hard it's been turned on. So let's go ahead and change that to DC voltage, and everything else on that looks good. Just going to change this as well to 3. There you go. That defines our DC voltage for channel 103. And I'm going to go all the way to the bottom, and I'm going to change channel 122, which is the current measurement. That's the current through the loads, and I'm going to define that measurement to be DC current. As you can see, everything else is disabled because it knows that that channel can only be used for DC current. So we select that, and we're going to do a similar thing, and PLC can be changed to 3. There it is. So now all of our channels are defined. So now look how many, by the way, how many channels we're not using. There's quite a few left in here in this module. We're only really using a fraction of them. And we can go back on the menu. You can go under control, and then you can see exactly what's defined for both of the slots. The slot 2 has another 7700 in it. None of it is configured because we're not using it yet. Let's go back under the menu again, and we can now define a scan. Because we have already defined channel 101, 102, 103, and 122, it has assumed that those are the ones we want to measure, which makes sense. We're going to go measure temperature from 101, 102, then measure DC voltage, then measure current, and go all the way back. It's going to do that once. This is a really simple scan, not very useful. So we're going to create some modifications so that it can do what we want it to do. So under settings, all of these things are there. You can change the setting of each of these as I did before. We already have defined those, so we don't have to change them, but we can change the scan properties. So how many measurements we want to make? Well, it's up to us, but let's go ahead and measure 100 points. This is just an example. Now here we have a chance to define how long to wait between the measurements. Now we don't want to wait too long, but we also don't want to do it very quickly because temperature is not going to change very fast. These things have high thermal mass. So there you go. 1 second is probably enough. 1 second is actually quite quick. In a real situation, you wouldn't measure it that fast. Anyway, that everything looks good. It gives you a scan duration, which is computed based on how many measurements you have and how long between the measurements. This is good, but how do we start the measurement? You can start it by pressing the trigger button or manually start it. But in reality, in a measurement like this, we want to only start it if the system has experienced an unusual temperature condition so that we can track the temperature when the fan comes on and look at the behavior of it like that. So let's go under trigger and define a trigger. By the way, there is just as many configuration capability here under this trigger menu as it was in the other one. You can define some pretty incredible complex set of conditions to start your measurement. We're going to do a really simple one. We're going to select to trigger based on a monitor measurement. So the instrument is going to monitor something in the background, and when it hits the right condition, then it's going to begin the scan. In this case, we're going to monitor channel 101 for temperature, and then we can say the start condition is if it goes above a high limit, and we can define the high limit to be, let's say, 30 degrees Celsius. So if the temperature goes above 30 degrees Celsius, it's going to start the measurement. That looks good. We're going to press OK. So it's going to take a brief moment to configure everything and make sure it's all assigned to the correct places, and it's ready. So now we can go ahead and see if we can run our experiment. Let's go back to the home menu over here, and right now we're not watching any of the channels. It's sometimes useful to see the channel that you are interested in live on the screen. So let's go ahead and select that we want to look at actually all of these channels so we can see them during the scan. There you go. So we have defined all the channels that we're watching, and we can go under the scan menu and we can start our scan. Now before I start the scan, I want to make sure that we have the current turned on so that the resistors continue to get warmer. So I'm going to go ahead and start the scan, and as soon as I do that, you can see that the instrument is just waiting. You see it's going pre-scan monitor. So the temperature is not above 30 degrees Celsius, so it doesn't need to actually begin the scan. And we can see that it is measuring 1 out of 100. So it's waiting. So let's go ahead and apply the current to the system, and as soon as I apply the current to the system, of course the temperature is going to start to rise, as you can see. Now, right now 22 degrees is perfectly fine. 30 is still quite some time away. So the system is going to wait, and we're going to wait for it until we hit 30 degrees Celsius. There you go, we're getting closer. So the condition was at 30, we're almost there, and there it is. As you can see, as soon as we hit 30 degrees, the measurement has begun. And it's going through all the scan. You can see all the measurements written over here. Here's 101, 102, 103. You can see all the measurements live going forward. So we're going to keep going and wait and see what happens. There it is. You can see we have measurement 14 out of 100, and the temperature is going to continue to rise. So let's see what happens as it gets closer and closer to the end. And we're almost done. 98, 99, and 100. So there it is. All the measurements are done. So let's see what happened to the data. There's a lot of ways to look at it, of course. By the way, I was looking at the wrong channel over here, but it doesn't matter because it was defined as the correct measurement. Even though I was looking at the channel I wasn't measuring, it didn't really matter because the data is being stored anyway. So I've changed that already. So let's go under menu and under graph, and we can look at the data in graph form, which is the most useful. And here we can change which data is highlighted so that we can see the statistical behavior of a particular set of data. So on 101 is the first channel. That was the channel we were measuring the temperature of so that we can trigger the measurement. You can see the minimum is at 30 degrees. That's because that's when the measurement actually began. That was our trigger condition. And you can see it went all the way to 41 degrees. But its behavior is very interesting because as you can see, it goes up and up and up, and then it flattens out at the very end, it goes back up again. So why is that? Well, if you correlate it with channel 103, which is our fan, you can see exactly why that has happened. So right over here, when the fan turns on, you can see that the temperature plateaus because the fan is cooling it, allowing a temperature to reach a different equilibrium. And when the fan turns off again, you can see the temperature rises. So we can see the correlation between those two. Now the other channel, the temperature continues to rise because the fan is not pointing to that point in the system. So this is one way you could detect that your thermal solution in a rack, for example, is not adequate for all the different locations in that entire system. This is one way to do it, and that's why people put multiple thermocouples in a complex structure so they can see the thermal behavior without having to model it, for instance, or do much more complicated ways of figuring it out. So this is very useful because we can see exactly the difference between those two temperatures now and do complete analysis. For instance, we can see that the minimum and the maximum temperature of channel 1 is between 30 and 41, and the minimum and maximum is between 31 and 46. So there is a 6-degree temperature shift between the two channels, which is readily available from the statistical data. Now the last channel, which is 122, is the current measurement. Now even though it looks flat over here, and that's because the scale is quite different for it, but if you look over here, you would be able to, if I find the right place where the temperature, where the current actually changed, which I forget where it was now, I think it's right over here, you can see that the minimum and the maximum is about 50 or between about 40 milliamps of difference. And that 40 milliamp of difference is the reason why this curve briefly changed shape. Let me see if I can zoom into it more. There it is. You can see, there you go. That's much easier to see now. You can see that the temperature the current went down a little bit and come back up, and there's a minor shift in the slope of the two channels due to that. That means that the system backed off how much current was being delivered to the resistors in order to reduce their power consumption. So you can even catch these tiny differences in the measurement because you have obviously 6.5 digits, so it shouldn't be a problem at all. And you can go back to looking at all of it at the same time. As you can see, there is so much to do when you can analyze the data and do statistical analysis and histograms and everything else that I talked about. This just really only scratches the surface, but gives you an idea of what you can do directly on the unit. Remember, I have not used the computer. This is all done purely on the instrument itself. And we're going to take a look at the PC software too. But having an instrument that can do so much on its own, built into the operating system that's consistent between all the models of all the source meters and multimeters, is a really big undertaking by Keithley, and I think it's going to pay off. And here we have the KickStart software, which is a platform designed to communicate with all of Keithley's instruments to extract information and do automation. So you could use this software instead of using the screen itself on the instrument to do the same kind of tasks and extract information directly on the PC. The advantage of this is that with the TSP interface or multiple instruments on LAN or USB, you can have a list of units here on the left, and then you can extract information from them in tandem and link them to each other for different triggering events and so on. So it can be quite powerful once it's configured. So here I have connected the DAQ6510 to the PC using USB. And if I double click on that, I get an option of choosing what I want to do with it. The DMM will be just a basic digital multimeter function, or I'm going to go do a data logger to show you kind of a similar way of doing what we just did using the instrument itself. So once you do that, then once you select that, you're going to get this window here, and then in this window you can then select all the channels. You can see all the channels that are available here on the right side. So let's go ahead and select channel 1. So as soon as I do that, I will get all the settings of that channel. By the way, the reason this computer is running so slowly is because it's connected to and recording at the same time. So it's not because the software itself is slow. So here you go. Let's say I want to measure DC voltage, and then I get this little window. These are exactly the same settings that the instrument gives you. One thing I like that it has is that you can do an instant measurement on the channel you have selected to get an idea of what it is you're actually doing. So if you don't know if you have 30 channels or 40 channels connected, you want to find out what it is you're measuring, this helps you do that. You can then add additional channels and then get, let's say, AC voltage from the next one, and then you can continue building this up. And once you're done with that, you save it. And of course, after that, then you can create a scan. Here I have an immediate scan. Let's say we want to make, I don't know, 10 measurements, pretty easy. And then we press play, and you can see it's going to go through and make the different measurements. Now, because we're measuring one AC and one DC, when it goes to AC measurement, it takes a little bit more time for it to settle and auto zero and do all the things that the instrument needs to do. But there you go, it's going through all the different measurements. You have a progress here at the bottom, and then after it is done, you can look at your result either on the table format. Here is the table format. Here's a channel 101, here's a timestamp, here's the value, channel 2 value. We can look at the graph and look at all the different things. It's really nice. Now, KickStarter is no longer free. I believe it used to be free, but I think it costs up to about $500 or so, depending on where you live, in order to do this automation. It's basically a competitor to BenchView from Keysight. So it's kind of a complementary software allowing it to do a similar kind of thing, but it is designed specifically for Keithley instruments and optimized for communicating with them. Definitely check this out if you want to have a PC with many instruments. I've gone through the KickStart software before. This is now version 2, so they have updated it quite a bit. And I've also shown you the scripting language. I'm not going into the details of that today, but you can see how you can write your own code, and it can become really, really powerful and create an entire automation system doing production line or research work that you might want to do in the laboratory. So it's pretty comprehensive. Definitely check it out. And as a last thing, we have to take a look at the apps button. Since Keithley has dedicated one button just for it, obviously they're very serious on taking these apps right into the next level. There's a couple of apps that are written already and the instrument comes with them, but the idea here is to develop more and more complex ones that can do more interesting things. And a couple of examples are very basic, but for instance, the clock, you will run that, it will get just a little clock. That's kind of cute. And you can then create more graphically interesting things. A couple of ideas they had was, for instance, to create an app that you can put a picture in and then put the location of all your sensors on the picture so you can see exactly hotspots in your chassis. And these are kind of interesting as visual feedbacks during your measurement. Something else that's useful that's shipped with it is this relay count. And this relay count tells you how many times the relays in your modules have been actuated. This is really useful because it can tell you how long you have until the module is essentially used up and you have to get a new one. Kind of gets you prepared for the future. You can view slot 1, which is a slot that I've been using a lot. You can see some of the relays. For example, relay 102 has been actuated over 1,300 times. So that's getting up there slowly. But of course, you have 100,000 measurements you can do, so it's not like it's going to die anytime soon. But nonetheless, this is pretty useful. We can end that app as well. And go under the apps, other things. You can have a grid. This is also really handy if you define some measurements. I don't have any measurements defined in here. As you can see, you have to set up a scan first. But once you set up a scan, you can then go ahead. Let's say I'm going to look at measure this one, and then that's a DC voltage or whatever it is, and then I can go back to the apps and run this grid again. And you can see it says 101 over there, and then you can start a scan. If I say yes, okay, it measures it, and then it shows you what's there. This is really useful. You can have a grid of all of your measurements going on live. So this app can be pretty handy. And I'm hoping that other apps can bring mathematical analysis and FFTs and other kind of interesting manipulation of data as you live measure them into the app ecosystem too, which is pretty useful. So I suggest you definitely take a look at that, because there's also a fuse checker in here, which is quite nice too. Tells you which fuse is dead by doing some internal testing. This is a nice introduction of this. Perhaps we'll do some more video exploration of these apps at a different time, but just wanted to point to it so you know that it is also available. And there you have it. I hope you enjoyed this extensive look at the Keithley DAQ6510 and that you learned something about how this instrument works. If you want to support this channel, you can always do it through Patreon and subscribing, of course, but you can also let the different manufacturers know that you watch these videos and that you use them to decide what instruments to buy. I do reviews across all manufacturers equally, and that gives a nice third view perspective of how they perform in some real life applications, and allowing the vendors know that you take these videos into consideration allows me to have a good relationship with them, so I can continue to bring you the latest and greatest instruments to review. Well, I hope you enjoyed this. I'll see you next time.